welcome to our final unit in the course, which deals with integration. And we start with antiderivatives. Think of antiderivatives as the opposite of the derivative, which seems pretty clear by the name. Well, let's consider this capital F of x. Capital F is an antiderivative Capital F is an antiderivative of little f of x if the derivative of capital F is little f. So really, this is the reverse process of the derivative. Right? Because the derivative of capital F is little f. So that means capital F is the opposite of the derivative, the reverse of the derivative of little f. So we say the antiderivative. Well, I made a little mistake in my speech there, didn't I? Because really, it's not the antiderivative, but it's an antiderivative. Turns out there's more than one for any given little f of x. We'll see that. So let's look at some examples. Let's say little f of x is the function 10, just that constant function, a horizontal line. Then an antiderivative of this f of x is 10x. Let's in fact call that capital F of x just to be crystal clear. And this is since if you take the derivative of capital F, you get little f back. Hence, capital F is an antiderivative of little f. So we're just going backwards with our derivative. Right? 10 is the derivative of 10x. Let's look at another one. Let's say if f of x is 3x squared, then an antiderivative is capital F, which is x cubed. So that's one antiderivative. Notice if I take the derivative of x cubed, I get back to 3x squared. But turns out there's more than one. And let's look at them now. Another antiderivative of f of x. Let's call this capital G. X cubed plus 1. Notice it has that same derivative, 3x squared, because the plus 1 just has a derivative of 0. And so it turns out you can always do this sort of thing. You can always just add any constant, and you have a new antiderivative. So that creates this large, infinite family of antiderivatives for a function. So the way I would put it to describe all antiderivatives would be x cubed plus c, capital C. Where c is any real number. Right, x cubed plus any real number is going to have that same derivative, 3x squared. So they will always work as antiderivatives. So that gives us a big, really infinite family of antiderivatives. Now, this is a little separate from that example. The family of all antiderivatives of a function little f so we call this an indefinite integral. That first adjective, indefinite, that is not going to be too important for us today, but it will be important later because we will see definite integrals later in a couple lessons. But for now, for this lesson, we're only talking about indefinite integrals. So here's what they look like. You have this big S-looking thing, which we call an integral sign. Means you're taking an integral of a function f of x. So the function you're integrating, we're finding the antiderivatives of, we call the integrand. Excuse me. And then you throw dx on the end. Now, there's a reason for this, but we won't get too into it right now. For now, just think of it as notation. It kind of bookends the integral. And it also tells you what variable you're dealing with. X is our main variable. So this indefinite integral, again, it's the family of all antiderivatives of f of x, which we call capital F of x, for some antiderivative, and then you write plus c, a capital C. Where c can be any real number, and then this gives you all of them. Now, in this course, we don't really get into why if f of x, if capital F, is a single antiderivative of little f, why does adding c for sure gives you everything? So we're not really getting too into that, the why of that, but it's true. So throwing on that plus c will give you all antiderivatives of little f. So for example, we take the indefinite integral of 2x and then write your dx on the end. Well, x squared is a great, very natural antiderivative of 2x, right? Because the derivative of x squared, if you go backwards, is 2x. Then just tack on that plus c. So this gives you all antiderivatives of 2x. since you have the plus c. Now, this leads us to our first rule of integration, power rule. Well, first we need to add this little thing. So as long as n is not -1, then we have a formula for taking the integral of x to the n. And this is the reverse of power rule for derivatives. You add 1 to the exponent instead of subtracting 1. And then you divide by that new power. And don't forget the plus c. So you see why we say that -1 doesn't work? Because if you plug it in here, you're dividing by 0. The formula breaks down. We will address that -1 case in a little while. But as long as the exponent here is not -1, then you get this nice little power rule formula. And again, it's the reverse of the derivatives power rule. Remember, for the derivative of x to the n, you would bring the power down and then subtract 1 from that power. Now this is the reverse. Well, first we add 1 to the power, and then we bring down, dividing by that new power instead of multiplying. All right, so first, why don't we do a quick check to make sure that this formula is true? You can always check to see that your antiderivative is correct by taking its derivative. And we should get back to the integrand here. So I'm taking the derivative of x to the n plus 1 over n plus 1. And we could write the plus c in there as well, but remember that derivative will just be 0. So it's not really of any consequence. All right, so this dividing by n plus 1, that's just a number, not a variable. Right, x is the variable here. So this divided by n plus 1, that's just a constant. Think of it like this. We can move it out of the derivative. And then we do power rule on this, our old derivative power rule. And so you would bring that power down, and then we have times x to the n plus 1, subtract 1 from the power. These n plus 1s here cancel, and the plus 1 and minus 1 cancel each other. So we get back to x to the n. So we indeed found a good antiderivative formula for x to the n. Let's do a quick example. X to the 5th dx. It'll take a little practice because we're used to the derivatives power rule. Now you've got to get used to the antiderivative power rule, where you add 1 to the exponent, and then you divide by that new power. So there's a bit of a reversal in the order that we do things as well. Let's look at our next properties of indefinite integrals. I'll call this linearity. Basically, these work very well with addition and subtraction, and also if you multiply by a constant number. Let's start with that one. So let's say k is some constant, like 2 or something. And you get the same thing if you just move that outside. So it works very well with those. So also if, well, let's use parentheses. Let's say I'm either adding or subtracting two functions and taking the indefinite integral or finding their antiderivatives. Then this is the same thing if you do each piece separately. It's kind of like how derivatives worked. So that integral over here, this integral over here, you can separate them in this way as two separate integrals. So integrals or antiderivatives, they work very well with multiplying by a number or adding and subtracting. Now, does this work with, say, multiplication or division? The answer is no. Just like how it worked with derivatives, you had to do some special rules when you were multiplying two functions or dividing. We're going to see that here as well, just not really today. Well, we actually won't go too deep into that because there's not really enough time left in the course. But that's a side note. All right, let's do a few examples. All right, well, for one thing, since I have subtraction, I can do this as two separate integrals. There we go. So then I can perform the power rule on each piece individually. Another thing I can do is move that 4 out. And now I'm free to do my power rule formulas on each piece. So I'm going to add 1 to that exponent. It's x to the 4. And you divide by that new power. And I'm actually not going to write the plus c yet, but you don't want to forget that in general. Let's do this antiderivative. That will be x cubed over 3. And now I'm going to write plus c. The reason I do this, I only write a single plus c, even though I was technically doing two integrals, is because you only really need to do one. If I've got a plus constant over here and a plus constant over there, then you could just bring those together as a single constant. So my point is, if you're doing multiple integrals in a row, you only need to write plus c once at the end. But you do need to write it once, so don't forget that. It'll count you wrong in Pearson if you don't have a plus c. And I think you need to write it as a capital C as well. Oh, and yes, these cancel as well. So that leads to a little bit of simplification. Let's finish that. This part, I'll say actually that the way I wrote it there is fine, but my personal preference is to usually write that 1/3 out separately, thinking of it as a times 1/3 instead of dividing by 3. But that part, don't worry about too much. That's really not a big deal. It's just personal preference on my end. Okay, let's say we're trying to find all antiderivatives of the constant function 12. Notice I don't explicitly have an x written in here, but it really is hidden in there because you can think of this as 12x to the 0. And then we can perform power rule on that part. Might want to bring the 12 out first. And then we can perform power rule on that x to the 0. So I add 1 to the exponent, divide by that new exponent, plus c. So just 12x plus c. Remember that power rule can be applied to radicals as well, so not just whole number exponents. So let's take a look at the square root of x, and then a weird one, the cubed root of x to the 7. So perhaps before we separate this out, let's rewrite those exponents. Or perhaps I should say write them in terms of exponents. Remember, the square root is the same thing as x to the 1/2. And a cube root, think of that as a 1/3. But I also have a 7 power in here. So that becomes 7/3. And now that we've written it this way, we're set up to use power rule. And I might separate these first as separate. Now, after today, I am just going to assume that we're familiar with this kind of step and not write out two separate integrals every time. Kind of like what I was doing with derivatives. You know, I kind of stopped writing ddx of this part plus ddx of that part. Think of this as like training wheels. But eventually we'll just start working on both pieces. Okay, now power rule. So you add 1 to the exponents. So 1/2 plus 1 divided by that new exponent. Okay, 7/3 plus 1. Just want to be clear about that. You do the 7/3 first and then add 1. And don't forget plus c. Again, even though I technically did two integrals here, you only need a single plus c. There's no sense in writing more than one of them, because they could just combine into a new single constant. All right, so 1/2 plus 1 that can be rewritten as 3/2. So x to the 3/2 divided by 3/2. Here, think of 1 as 3/3, which will give us 10/3. And now that we're dividing by fractions, let's think of that as multiplying by their reciprocal. That's a bit more tidy. And there, that is all antiderivatives of our function square root of x plus cube root of x to the 7. Let's discuss a new kind of function, exponentials. And we're just going to focus our energy on the e type, like e to the x. So antiderivatives of e to the x is just e to the x plus c. Because remember, e to the x is its own derivative. So derivative of e to the x plus c here will get me back to just plain old e to the x. Now it gets slightly more complicated if I have some number times x here. In that case, the antiderivative is same thing back, but then you divide by that number k. If you don't believe me, you can check my work by taking the derivative of this, and you should get back e to the kx. You would use chain rule for that. Quick example. Finding the indefinite integral of 9e to the 3t dt. So I'm using a new variable now, but doesn't really matter as long as I'm consistent calling this t. Right, so we can bring that 9 out. And then take this antiderivative. That would be itself divided by that 3. Don't forget the plus c. And then you get a little canceling here with the 9 and 3. Now let's address that power rule case, except when n is -1. If I scroll up for a second here. The power rule only works when n is not -1. So let's look at now, what if n is -1? So it'll be a new formula. And this isn't anything new yet. I'm just saying these are different ways of saying the same thing. The result, well, does this look familiar as a derivative to a certain function? Should remind you of ln, natural log. But I'm going to throw in something maybe a little unexpected. natural log of the absolute value of x plus c. And let's discuss that part real quick. So why the absolute value around the x? Well, remember, absolute value, it takes any number and gives you the positive version of it. So if you plug in a positive number, there's no change at all. But if I plug in a negative number like -1, the absolute value changes it to 1, the positive counterpart. And the reason we need this is because remember that only certain numbers can be plugged into a natural log. That is, only positive numbers can go in. So by putting an absolute value bar around the x, I'm ensuring that only good stuff gets plugged in. You still can't plug in 0, but that's fine. You can't plug in 0 for this thing either. So I want to say note that plain old ln of x is only defined for x greater than 0 and positive numbers. So then this absolute value allows for negative x values to be plugged in because we take the absolute value of them. Maybe I should say that. These absolute value bars allow for negative x values. There we go. That's desirable for us because the integrand here, 1 over x, that also has negative x values. So including the absolute value bars here allows us to be all-inclusive for all x in the domain. Now let's do a quick check. Make sure that this is right, even with the absolute value part. Well, the only thing we really need to check is when x is negative. If x is positive, then these absolute value bars are doing nothing at all, and they don't need to be there. And then, yes, the derivative of natural log is 1 over x. So we don't really need to check that. What we need to check is check for when x is negative. Make sure that those absolute value bars work. So assuming that x is a negative number, then that means that the absolute value of x is the same thing as negative x, right? Because if I take the absolute value of, say, -1, that will flip it to 1. And 1 is the negative of -1. So this negative means that flipping over is happening from negative to positive. And so now, if I take the derivative of that, I get 1 over negative x times the derivative of negative x by chain rule. And indeed, we get 1 over x. Therefore, natural log of the absolute value of x works as an antiderivative, even for negative x values. And sometimes you have examples like this which look really complicated at first. So at first it may appear that we don't have the tools to do this, but that's not true. We do have the tools to do this. The main trick is to write this as a sum of two separate fractions. The way the fractions work, you can do this. Let's go down here. I can split these up as long as I keep that common denominator. And while we're at it, why don't we rewrite this square root of x cubed in terms of something that'll be easier for us to work with? X to the 3 halves. Because we can do power rule on that. So now that we've split these up as two separate fractions, I can do a little canceling. So that reduces to 27 over x. And for this part, remember you subtract the exponents. Okay. So how about we solve that other part first? Or just simplify this, I mean. 3 halves minus 4. If you think of 4 as 8 over 2, then 3 halves minus 8 halves gets you negative 5 halves. And now we've simplified things enough so that we can take an antiderivative. Oh, you know what? I could probably do even a little better here. If I bring that 27 out. So then we can see, all right, this is the ln case. Technically ln of the absolute value of x. And this part, we do power rule. So if you add 1 to this exponent, that will get you negative 3 halves. Then you divide by that same new power. Don't forget your plus c. And let's simplify. I don't really want to divide by a fraction. And I've got a negative here, so it's minus 2/3 x to the negative 3 halves plus c. Let's finish with a word problem. Start to see a little bit of practical application of these things. Talking about the marginal cost. Remember marginal, think derivative. So I'm basically saying the derivative of the cost function, cost of producing X units of some product, This marginal cost is C prime of x equals 0.03 times e to the 0.02x. Turns out we will need a little bit more information if we want to find the cost. And I'll explain. Well, this thing called the fixed cost, which just means the cost when x is 0, when no units have yet been produced. It's just some fixed underlying cost of everything. Is $5. And before I write the next thing, just want to point something out here with this. We call this the initial value. I think of it as some extra little bit of info at the start of the problem. And we'll talk about this in a bit, but I just wanted to point that out first. So that little extra bit of info is called the initial value. And so the goal is find the cost function, capital C. Again, we know the marginal cost, the derivative, and we know a little bit of extra information, that initial value. And then that will be all we need to find the cost. So let's call this C of x. It's going to be an antiderivative of that marginal cost, right? Because marginal cost is the derivative of cost. So let's fill in that information. 0.03 e to the 0.02x dx. All right, so the 0.03 goes out. And then we have an e part we can deal with. Its antiderivative is itself divided by that extra constant in there. And well, instead of plus c, I'm going to write plus d because c is already being taken up. So it makes more sense to call this plus d, just to avoid confusion with the letters. So that plus d, that's just some constant. So in this case, this is some particular real number we need to find. Right? Because we could have some plus 2, plus 1, whatever, and that would give the same derivative. So we don't yet know what this is. And when we're doing a word problem, this plus d is just one particular thing. I'm not really interested in an infinite family of antiderivatives. We're looking for one particular one that works. So the way that we find that d, that will finish the problem for us, is through this part. That extra little bit of info, the initial value, that's how you find your extra constant at the end. So we know that when x is 0, we have a cost of $5. So I'm trying to find D. Well, C of 0. So plugging in 0 for x. I know that this whole thing must be $5. And now this is how we can find that missing constant. So e to the 0 power is 1. So I'm still left with this 0.03 divided by 0.02. And why don't we go ahead and simplify that part? I probably should have done that earlier, but it's okay. Well, you could use a calculator. That's fine, but you could also think of this as 3 divided by 100 over 2 divided by 100, and those over 100s cancel. So it's 3 halves, 1.5. So I'll throw that into my final answer. But now we can solve for D just by subtracting 1.5. So that's the constant that was missing in my cost function. And now we can finish that. And yes, I will want to, in the end, rewrite that 0.03 divided by 0.02 as 1.5. So C of x is 1.5 e to the 0.02x plus my constant 3.5. So remember that if you take the antiderivative, you need to write a plus C or plus D in whatever letter you want, because there could be some constant there. And then the way that you solve for it is through this extra little bit of info at a particular moment. That's the initial value. Great. Well, see you next time.